Good to hear. There we go.
And we also brought some toilet rolls.
You bought some what?
Toilet rolls.
Oh, good. Okay, cool. Well, we got a lot, so we should be good to
He
go.
dropped them all out of the car.
Oh, no. Did he really? And you just left him out there to clean him up, huh?
It was very cold.
Nah. There's big sister language if I've ever heard it. Well, you know.
This morning.
I was like below freezing in my house.
It's gonna get to 27 tonight. 20.
He made me take the dog out, and I didn't have any shoes or socks.
Ah, how mean. How cruel. Now you paid him back, huh? Yeah, you might have to like scoot yourself one direction or another to avoid all that.
I don't know. Wow.
There you go. Well, Carlos and Nico are not gonna be here because they're actually on they're on extended vacay. So really, it's just Lewis and Emma that are still left to come. Everybody have this? Let me see, you asked about 13 units, yes,
I
Caitlin
got
turned in.
97%.
Caitlin turned in 13, is that what you're asking about?
Yeah.
Okay, yeah.
Can I give the girl both for everything? Or
You did it for 13?
yeah, it took me like around 5 hours to answer it.
Goodness.
It was like so tough.
Yeah, you can do that. You can, if whatever you have, just turn it in over there, okay?
Turn it in over there.
Over there where you put stuff, you know. Hey, Louis, you here with her? Hi, it's $2. Definitely going around. We have a friend of the pharmacist, and he said yesterday there's a lot of flu. Because college kids brought it back
I
home.
couldn't just where?
Yeah, Lewis had RSV, we think. Oh, we found out he was allergic to the antibiotic.
Oh,
Just like me.
What they put you on?
Penicillin.
No, and
Swell up.
no, look, he's got a rash.
Oh, no. Oh, it's
not
not
contagious.
I can't take it either, that very same reason.
Yeah,
So that's
My
why
mom
I
and dad
got
are
all
both-
red. Yeah, that's no.
my mom and dad are both.
Yeah, Junior's fine. Yeah, that's no fun, man. I've only got like 2 classes of antibiotics that I'm not allergic to, so I literally feel your pain. Like I know, I am so
This is the
sorry.
first time he's taken them, so we found out he was allergic, and I took him a few years back, and same thing happened to me.
Oh yeah,
So, can't take 'em.
yeah. My kids. I don't think my kids have ever had.
I love that pillow.
And cute, thank you. I don't think either of my kids have ever had penicillin because both of us are allergic. Both
And you
Jason and I are allergic.
Amoxicillin?
It's a penicillin. Yep. I can't do any of the Cillins. I can't do sulfa, which is another big class. So basically, it's like I can do like Cipro and Keflex and that kind of thing, but the other stuff is bad, no good. And I can't do. There's something called amantadine. It's like before Tamiflu. It was an anti. I'll bring that down a little bit. It was an antiviral. I only had the flu one time in my life. Not one day. And it was when I was in college,
Very recently.
and it was, pardon my shoes. It was when I was in college, and I was, it was going around. And so they recommended that we get the flu shot, which I normally don't get. So I was like, all right, so I got the flu shot.
Yeah, I got the flu shot.
And then I got the flu 2 days later. So yay for the flu shot.
I mean,
But
they
anyway.
gotta update all these things all the time.
Yep.
You just-
I got the flu like 2-3 days later, and then they gave me amantadine to try and make the flu go away faster, and I was like covered in hives. So what could have been minor turned into like 2 weeks of sick. That wasn't fun. Well, okay. It's after 10, so even though Emma hasn't made it yet, we'll go ahead and start. So we only have 2 more lessons. We are wrapping it up. Hope everybody had a good turkey day. Did everybody get turkey?
Lesson 16 is a review.
It's we've got, well, no, yes. I was trying to think of which is which.
I just felt like
16 is like 2 days, exactly 2 days after my birthday.
There you go. Yeah, we've got review and we've got a whole day of nothing but review before midterms.
I got a sign over here. It's my name.
So we're going to talk about energy today. All right. So energy and work. So what is the ability to do work? All right, Darcy, that would be energy, which makes perfect sense because if you ever say, I just have no energy today, you don't feel like you can do any work, right? I mean, shoot. And then work is the transfer of energy. Because we talked about how, machines do work. And most of the time, what you're doing is transferring one form of energy to another form of energy. So we're going to talk about the different forms of energy today. And I had some really fun videos integrated into this slideshow. And then when I went to double check everything this morning, they wouldn't play. So we're going to have to like zip in and out of my PowerPoint a couple times, but it'll be fun anyway. All right, so energy and its forms. So energy and its forms, energy can be largely divided into two big types. Lewis, what do we have?
Kinetic and potential.
There you go, kinetic and potential. All right, so if you look, kinetic can be further subdivided into mechanical, thermal, sound, electric, and radiant. What does it mean? What does kinetic mean? What kind of energy is kinetic energy? Eunice?
Of any object moving.
Yeah.
its mass and
There's your key word. Okay, so kinetic energy is energy in motion or energy of motion. So it's motion related energy. Okay. So you ever hear like there's toys? I actually have a whole big set of, they're called Kinects. Great word. They're toys that move, right? So kinetic has to do with actually moving. All right. And then you have potential, which is exactly what it sounds like. If I say Lewis has the potential to play in the Masters one day, then there you go. All right. So then what does that mean? Potential. What does it mean in that case?
inside, skill, but I just need to work on getting better.
Yeah, you got the ability to do it, right? So it's like you're not doing it yet, but that you have the ability to do it. So potential is stuff like gravitational, chemical, nuclear, and elastic energy.
I was trying to read this. I was doing this last night while I was watching TV. I was in the basement trying to read the fine print.
Oh, yeah.
I just couldn't.
Too tiny. Well, it's a little bigger over here so you can see them. All right. So we said that kinetic energy is energy of motion. All right. So kinetic energy depends. The kinetic energy of any moving object depends upon its mass and speed, which makes sense, right? Because we talked before about, think about when we talked before about Newton's laws. And we talked about, what does F equal? ma, right? So it's mass times acceleration, and acceleration is given in like per second, right? Like meters per second.
Our new algebra book, it's based around physics. We're learning it through physics.
Oh,
and,
cool.
I think today we had K equals something T.
Okay.
I forgot. That was early in the morning.
Yeah, it's early in the morning. So yeah. So basically, something that has more mass is going to have more energy, and something that has less speed is going to have less energy. So think about like the energy involved in an accident where a school bus hits a telephone pole versus when a Mini Cooper hits a telephone pole. And say the school bus is going really slow, like 1 mile an hour, or the Mini Cooper is going like 65 miles an hour. You can envision the differences, right? Like if your Mini Cooper is going really slow, you're going to have very little damage. And if your school bus is going real fast, you're going to have a lot, right? All right. So we have our forms of kinetic energy, and here are our major forms. This is what we talked about. So you have mechanical, thermal, sound, electric, and then radiant or electromagnetic, which they're the same thing. So mechanical energy is just what it sounds like. So what kind of energy is this? Associated with motion and position, Eunice?
Is mechanical.
That's mechanical. Okay, so it's associated with motion and position. Yes.
Mechanical energy is associated with motion, and it says a
Period.
dot period
Oh.
position.
Oh, yeah.
Got you there.
You found one there. Yep. So, yeah, Yeah, I guess
You gotta solve the brownie. Also,
so. Mm-hmm.
where did you get that garland? That is.
I got that. Okay, thank you, because it's freaking adorable, right?
I know.
I think it was Hobby Lobby. I
wonder-
think it was I just saw it a couple weeks ago wherever I was, and I was like, that is too hilarious. The underpants do it for me, the elf underpants. So I had to get it. Yeah. I had a different one up there before, but that one wins. That's too cute. So yeah. So we're talking about associated with motion and position. So what kind of energy is the total potential and kinetic energy of an object's microscopic particles associated with its heat? What do you think, Darcy? What's that?
Thermal.
Thermal. Okay. So do you know, does anybody remember the definition of temperature? We're going to talk about this next week too. Does anybody remember it? So temperature is a measure of something. It's the measure of the movement of the particles in an object or substance. So in that case, you're talking about the movement of particles. So since it's movement, this is why thermal energy is a type of kinetic energy. So the more your particles move and the faster your particles move, the warmer something is, right? Like if you heat something up, it causes the particles in it to move faster and move more. So that's why it's kinetic. You may not think of heat as kinetic, but it is, because it has to do with the motion at that, particle level, which is different than what we usually think about. Heat is actually the transfer of that thermal energy. So like if you touch that glass table, like if you put your finger on the glass table, about what temperature do you think it is?
Room temperature.
Room temperature is right.
70.
Yeah. Now touch to the couch cushion or something like that. Which felt colder to you?
Couch cushion.
The couch cushion felt colder
I
than
was
the table.
leaning on this because we heated it up.
Yeah. So usually this has to do with conduction, and you're going to read about this next week, but it's, the couch and the floor and the glass, they're all what are we at? 67 degrees. That's what they are. Okay. But glass is a better conductor of heat. So when you put your hand on there, the reason it feels colder is because more heat is leaving your hand than when you put it on something that's fabric, which is an insulator. Less heat is leaving your hand. That's why you put a blanket on you, because it's an insulator, right? Keeps you warm. So what kind of energy has to do with vibrations transferred by waves? Eunice, what you got?
Vibrations.
Transferred by waves.
Yeah.
What's this one? What do you think it might be? No, not this one. What do you think? Lewis, what do you think? Look at the picture. What do you think it might be? It might not be in your nose. What do you think? Not electrical.
Chemical.
No, sound. So sound energy is a kinetic energy. Yeah, sound. Yeah, it might not be in there, but it's one you should know. So sound is kinetic because the waves, sound waves, are moving. Okay. So it is a type of kinetic energy, sound, right? And sound you might not think of as energy really, but it is. I mean, it's just as much energy like light energy. That's another kind that we'll get to in a minute. All right. So what kind of energy is associated with electrical charges? All right, Lewis, what you get? Electrical energy. Okay. Now in this case, why would this be kinetic? What's moving? What do you think?
Because
Heat? What's moving in yeah.
You have an L there and
Oh,
an L there.
Oh, okay.
All the
All right, we'll worry about that in a bit. What about what is moving? Kinetic. So it's to do with motion. So what's moving with electrical energy?
Light.
Light. We had we had mechanical energy where you can see things moving, right? We had sound energy where it's like the waves are traveling through the air. That's electricity.
Wait. Is it electrical charges?
Electrical charges, right? Electrons themselves, right? Electrical charges, that's right. That's where the motion is. Very good. So there's motion with kinetic energy. There's always, because kinetic energy has to do with motion. So Yes, you've got electrical charges that move, usually along a wire, hopefully, because that means you're controlling it, right? And not like,
Like a telephone.
yeah, like that. So then what's this last one? Travels through space. All right, Eunice, what you get?
Is that nuclear energy?
Not nuclear.
Electromagnetic.
Electromagnetic, yes. Don't you love, look at her. She is at the beach
Haven't thought
in
of
her
that.
pink bikini, right? Because that's pretty awesome. So yes, electromagnetic or light energy. Now light is special because light travels as waves, but it also travels as particles. And we're going to talk about it next semester a little bit. We're going to have some discussion about light and optics and all kinds of wave theory, all kinds of fun stuff like that. But this is why you can get a sunburn. That's energy, right?
Yeah.
And it's all those little, the particles from the light are always moving. Light's moving as waves and as particles, which you'll see. Like I said, next semester we'll do some experiments. We can actually see it. It's pretty cool. But yeah, so there's your kinetic, is that it's moving, right? Where does this kind of energy come from?
The sun.
Yeah, it's coming from the sun, right?
You
Yeah.
get skin cancer if you don't.
Yes, it's very true. So there, you have to keep in mind though, when it deals with this electromagnetic, there's other wavelengths out there that aren't necessarily generated from the sun. Like we can generate them, like X-rays, right? But in that case, these are on the spectrum, but they're not visible. So visible to us is the visible light spectrum. So that's like, your rainbow, your Roy G. Biv, all those colors that you see. But there are electromagnetic waves all around us right now that we can't see that are doing all kinds of things. We've learned to harness it. Like we use it for radio and we use it for, microwave, all kinds of stuff, right? There's all kinds of stuff going on that we don't see, and it's there. And we'll be talking about that, like I said, next semester. Okay, so here's your kinetic energy. If you want to find out, how to solve a problem involving kinetic energy itself, then this is the equation that you use. Okay, so basically it's 1/2 mv squared.
mv squared.
Yeah, very good. Okay, so you have the mass of something, you have the velocity of something, and you can put those numbers together and get an answer. We're not doing that in particular, but I wanted to make sure that you knew that there is an actual formula for that you can use. So now when we talk about energy that's stored versus energy that's actually moving. So what's this, Lewis? This is potential. Okay, so let's talk about potential. So potential is energy that is stored as a result of position or shape. And it can also be stored, it's kind of hard to describe, but it can be stored as like, on a molecular level, let's just say. And we'll get to that in a minute. So here are major types: gravitational, chemical, nuclear, elastic. Okay, so chemical is the one that you have to think about on a molecular level. Gravitational has to do with position, right? And both nuclear and chemical really are your molecular level stuff. And it has to do with bonds, and bonds that want to break, bonds that will break when certain chemicals come in contact with others, that kind of thing. And when a bond breaks, it releases energy. When a bond is formed, it usually consumes energy. And then elastic is the other one. And this is the one that, we think about it as just like elastic itself, like the material, but there's lots of elastic energy. Have you ever seen anybody build, there's traps you can build like with tree branches where you can like pull them down.
And they like do the trap.
Yeah, all that. Yeah. Or like my granddaddy used to tell my daddy to go get a switch off the peach tree because I swip it around. You're right. So that's all elastic energy. All right. So what is this energy that depends on height, Darcy?
Gravitational.
That's our gravitational. All right. So gravitational energy is going to depend on your height. Obviously, the higher you are, the greater your gravitational potential energy. If I took an egg, all right, and I held it over my kitchen counter about this far off the counter, and I dropped it, do you think it might crack? Yeah, it might. It might. How about here? Maybe. How about if I dropped it from this side?
It will.
It's going to crack, right? Okay, because the energy is going to increase with the altitude or the height. Let me show it's not an important text message that I need. No. Okay. So yes, this is our gravitational potential energy, and it's going to depend upon the height of an object. So an object's gravitational potential energy depends on its mass and its height and the acceleration due to gravity. So let's think about all three of those things. So we just said height. We just gave an example of height. Where's an example? Can somebody give me an example of where mass would affect your gravitational potential energy? What do you think, Darcy?
Your weight.
Mm-hmm.
The weight of the object.
So give me like an example. Can you create an example in your head? Like compare maybe two things of different mass?
Say a feather falling from 500 meters in the air
Uh-huh.
versus a 500-pound boulder.
Oh, yes.
One of which would have more resistance, the one would have less.
Yes, that's very good. Okay, those are very good examples. And one other thing to consider when you're discussing gravitational potential energy is this acceleration bit. Okay, now what kinds of things affect acceleration? Gravity is the big one, right? What else might affect it? If you were falling from a plane, but you wanted to slow your acceleration to the ground, what would you use? Okay, why? What
Because
does it
it
do?
has low weight.
It traps the wind like
Yeah,
inside of
it does, right? They have a big surface area, right? And they trap the air in it, and that slows things down because they spread out. I was just about to say, so over break, we went to iFly. Drew got a gift certificate from his grandparents last Christmas, and we just hadn't been able to work it out. So we finally went. So that was my only skydiving experience. It was contained within a wind tunnel, right? You're indoors.
I said I'm going to do that with my mom one day.
It's fun. It's totally worth it. Do it. And guess what? They do field trips. So I'm going to be thinking about it because they do like really cool educational field trips where they involve physics and all kinds of stuff. And they bring it in and you get to go in and you get to do the skydiving. But they teach you how to do all kinds of interesting things. If you stay long enough and you learn, like you can take classes and learn from them, they'll teach you to do tricks.
20th to the 25th of December, because between that I'm going to be in New York.
Oh no, I wouldn't do it this soon. But one of the things I thought was wild. So when they tell you to go in and you put your hands up like this, right? And you have to keep your chin up, and you just kind of gradually bend your legs a little bit behind you so that you're kind of like this shape.
Mhm.
Okay, so when the guy went in at the end, he was showing us stuff. He did like a demo. So he went in and he's floating there. He was staring at us. He's like at eye level. And then he did this crazy thing. He hollowed his body. And what do you think happened?
He went up a bit.
He went way up. Yeah, he hollowed his body and went right up to the top of the tunnel. And then he arched and he came back down because he was changing his shape from this shape to this shape, right? So with this shape, it pushed him up. And when he changed his shape,
So
he
that's
came back
good to know
down.
if you're ever like
Mhm.
falling and you want to slow down, like
Yeah, you can hollow your, yeah, that was, yeah. And the other thing that was wild, so they taught us how to turn. So if you're floating, right? Imagine you're floating like you're roughly like this, you're a little bent, right? You're floating. This is how you turn. You barely move your hands, and that is enough to turn you.
oh,
It
that'd be
was wild.
So funny. My mom once went on a hoverboard. She went, and then
Oh
she-
yeah.
You remember this, Lou? She went on the chair. Her nose.
Oh,
I would be
I
scared.
don't think she thought it was funny. No. All right, so here is your formula if you want to try and do math with gravitational potential energy. So you need mass, you need gravitational field strength, you need height, and you need gravitational potential energy. Well, that's what you're going to find is gravitational potential energy. What do you think is gravitational field strength? What number would you, what would you use for that? Do you?
G.
Yeah, you'd use G. Very good. What's G? Do you remember what it is? Do you remember?
Is it
Looking good. You're smart. You're looking to see.
Gravity.
It's the gravitational constant. Does anybody remember the value of G?
G, like G equals?
Yeah. Do you remember what it
G
equals?
GPE divided by MH.
Yeah. What's the value of G on Earth? The average value of G, which is obviously going to be a bit different between like Denver and New Orleans, but it's 9.8 meters per second squared. Remember that? So sometimes for mathematical equations, people just use tens. Yeah. There you go. All right. So what type of energy is stored in objects that are stretched or compressed? Okay, Eunice, what you got?
Elastic.
This is elastic. Very good. Okay, stretched or compressed. This is the kind of energy that is involved in earthquakes. Because in that case, what you've got is usually some
Stretch.
there's stretch, right? There's friction in between the rocks, and they're not very elastic. They're very rigid, they're brittle. And since they're not elastic, they don't stretch a whole lot before they shift and move, right? So this little guy, he's like doing stretchy exercises, right? So there's a formula for that one too. And this is your elastic potential energy is 1/2 of the spring constant and times the extension squared. The spring constant is something you have to know for whatever material you're working with. It can be an actual spring or it can be some other kind of material, but you have to have that value in order to start. Okay, then what's this one? All right, Darcy,
Chemical.
this is chemical and it's stored in chemical bonds. All right, so this is one of your molecular ones, chemical and nuclear. All right, now chemical energy, we tend to think of, like we like to think, oh, batteries, right? Batteries are chemical potential energy. You put a battery on the floor, it's not going to do anything. It's just going to sit there, right? But you give it away for those chemicals to start moving, and then you get, once it's moving, what do you get? Electrical, which is kinetic, because then it's moving. Your electric charges are moving through it, right? But if you just leave it there, it's chemical potential. The most best example of chemical potential, probably that you deal with every day, is food. When you eat food, your food is potential chemical energy. Your body takes it in and then uses that chemical energy with aerobic respiration. So this last one is obviously, what's it, Lewis? Yeah, this is nuclear. Okay. Nuclear, nuclei. This is one of those words, people get it wrong all the time, but nuclear, nuclei. So always remember that, because that's to deal with the nucleus. Nuclear energy is stored in the nuclei. What do they do with nuclear energy? How do they make it? What are they actually doing? You know? So they're going into a nucleus of an atom, usually a very heavy atom, like uranium or something like that. That's a very heavy element, big high number on the periodic table. And they're going in and they're splitting that nucleus. It's fission, right? And then there's also fusion, where they're putting them together. So remember when I said before that putting the building bonds tends to take energy and breaking bonds releases energy? Remember when I said that before? So when we do chemistry next year, you'll see that a lot. That's why, like, sometimes when you there's some chemical reactions that make things feel cold, like you touch it and it's cold, like those ice packs that you like keep in a drawer, but then when you pop the little bubble inside and shake it, it suddenly gets really, really cold. You ever use those before? Those ice packs? They use them for sports all the time. A little plastic bag. And inside the bag, there's like a chemical you can hear shaking around like little beads. And then there's like another bag inside the bag. And you squeeze it real hard, it breaks the interior bag. And when those chemicals come in contact with each other, it gets cold. And that's usually because they're bonding together. So they're taking in
ice packs,
right,
cold ones when you snap them.
Yeah, like that. Exactly. So they're taking energy in order to bond. And when they're taking in that energy, that's what produces that cold feeling, because they're pulling thermal energy in, right? So other things like the hand warmers you use when you go skiing, same idea, but you break them open and suddenly they're warm. That's that. In that case, what you're doing is you're breaking apart bonds. It's releasing energy and things are getting warm.
Those are also great in the winter just to put in your glove.
Oh, yeah. Yeah. People use them when they go skiing and stuff. They're great. But yeah, so nuclear energy, what you're doing is you're breaking that nucleus apart. And that's really, really different, because in that case, you're doing something way more complex than just breaking a bond. You're breaking an actual atom. He's okay. He's just dealing with the poor allergies, man. Drug allergies are the worst. Oh. All right, so energy conversion and conservation. So let's talk conversion and conservation. All right. So the law of conservation of energy states energy cannot be what? Who wants to do it for me? Darcy?
Energy cannot be consumed. No.
You know it. Okay, what is it, Eunice?
Energy cannot be destroyed.
Or?
Oh, wait.
2 parts.
Energy cannot be created or destroyed.
Yep, it can only change form. Okay, this is the same thing it's the same basic law for mass, matter, energy. So Insert your word. Mass, matter, or energy cannot be created or destroyed, can only change form. Well, conservation of mass is more like just can't be created or destroyed. But matter, if you have an ice cube and you put it on the table and you come back 3 hours later and the ice cube is gone, did we destroy the matter? No, what
It
happened
just
to
changed
it?
form to a liquid.
It changed form to a liquid, and then what happened after that?
It would just evaporate.
It evaporated, so now it's a vapor, right? So you didn't destroy that matter, it's still here. You didn't get rid of those atoms. All the atoms, with the exception of some very crazy experiments, all the atoms that exist have always existed since Earth has existed, and they just cycle around. Like everything that you're made of came from something else, right? Like you're made of nutrients that came from soil, plants, meat, whatever you ate, right? And when you die, it's all going to go right back into the earth, or if you get cremated, it'll turn into heat. But still, that energy and that matter, it doesn't go anywhere, right? It just gets cycled around and around and around. So yes, can't be created or destroyed. It only changes form. So energy can be converted from one form to another. Energy, what is the process of changing energy from one form to another, Lewis?
Conversion.
There you go, energy conversion. So you're going to change energy from one form to another. Now, this is what you're going to be doing when you build your Rube Goldberg machines. You're going to be changing energy from one form to another a lot. So what kind of energy, oh, that should say clock. Look at that. Hold on, I have to fix that. That's a bad one. Clack. How did that pass? I don't even know how that passed. There you go. Spell check didn't catch it. So what kind of energy in this clock is converted into sound energy? What do you think? Darcy, you want to guess?
The hands are ticking.
The hands are ticking. Yeah. This is an old school clock. So what do you think, Lewis?
Kinetic energy?
Kinetic. What do you think?
I think it is mechanical energy because it's in motion.
Okay. Those are all great guesses. All right. So it's mechanical.
Yes.
So mechanical energy in this clock is converted into sound. And the reason is, see this little dingy thing right here? See this little thing?
Yep.
So this thing swings back and forth, and when it hits the bells, it makes a sound. Now, what causes it to swing back and forth? Does anybody know in these old ones, these old clocks like this? It's not the kind you plug in. It's a spring. You wind it. You wind the clock, so you've got elastic potential energy. And then as that spring unwinds, sooner or later, it produces kinetic energy as the hands move, and then it'll also let go of that the little thing that holds the hammer still, and then the hammer goes. All right, so how about this one? What kind of energy was in your breakfast? All right, Eunice?
The nuclear energy.
In your breakfast? What you eat, uranium?
Electric.
Hang on, no, we've guessed what is it? Not electrical.
Wait, kinetic. Chemical.
Chemical. Okay, chemical. All right, so your chemical energy in your breakfast. And what's it get converted to throughout the day? Lewis?
And
Yeah, what kind of energy?
potential.
Potential energy. Okay, what else? Kinetic energy. What else?
Um,
He's struggling. He's gonna get it. So yes, you get thermal, yes, and mechanical and kinetic. So you're mechanical as you're moving. Okay, what happens if you move a lot? If you run a lot, do you get cooler?
No, yeah.
You get hot, right? And that's part of the chemical reaction going on in your body. So that energy that's being released in those reactions comes out in the form of thermal energy, and it comes out in the form of mechanical and kinetic energy as parts of your body actually move, right? All right. So what kind of energy is in the hair dryer? And what's it converted into? What you get?
Electrical, because
Okay, yep. It's plugged in. All right. And then Darcy, what's it?
Thermal.
Thermal and also kinetic because it spins that fan, right? The little fan in there blows around. Right. Okay. How about this one? What kind of energy is in this flashlight battery? Lewis?
I
Well, what's in the battery?
chemical.
Chemical, and then it is converted. You said, yep, light. So thermal and electromagnetic. Now, thermal, assuming it's not an LED. I mean, LEDs, yes, but they produce very little heat, which is why we use them so much now. Whereas incandescent bulbs, old school ones, they get hot, right? Like if you touch a light bulb, that's a regular light bulb, an incandescent bulb, it's hot. Whereas if you touch an LED, usually not that warm, right? All right, so what's this one? Gravitational potential energy of the water balloon is going to be converted into what? What'd you get, Eunice?
It's converted into something. It's
This should say as it falls. Look at that. Miss stuff in here. Yeah, it's going to be converted into, well, it's gravitational potential and it's kinetic as it's moving, right? Okay, so fuels. Let's whip through these. So energy resources exist in limited quantities. What kind of resources exist in limited quantities? Darcy.
Energy resource.
What kind?
Oh, so sun, wind,
fossil fuels.
Non-renewable. That's the word we use. Okay, so non-renewable. These are the ones that they can't replace them, right? So this would be stuff like your fossil fuels, yes. Oil, natural gas, coal, uranium. These are all forms of potential energy, chemical potential energy, and they're not renewable. I mean, technically they're renewable, but not in your lifetime or in the next couple centuries, right? It takes a long time to make oil and coal. So what are the ones that can be relatively quickly replaced? If non-renewable are the ones that can't be renewable, right? So, and these are all forms of potential energy too. So renewable energy, and some of these are not, don't have to do with like replanting trees or recreating coal, for example. This one would be, yeah, hydroelectric's the type of, we call it renewable. So basically, what kind of energy is this using? Water. What kind of energy is involved with water flowing?
Gravitation.
Yes, gravitational is spot on. Yes, it's gravitational energy that's used. Okay, how about this one? What do we call energy from sunlight? What is it, Darcy?
renewable.
It's renewable. What kind of energy is it?
You take this.
Solar. That's what we call it, right? Solar energy comes from the sun. So what kind of potential energy is it then?
Electric? No, kinetic.
Solar, electromagnetic, or light. So this, in this case, it's it's tricky because technically this is a kinetic energy, right? But once we take that kind of energy and we store it, then it becomes potential. But it's really, in that case, it's really chemical after it's been stored. So what type of energy is thermal energy from Earth's surface? What do we call that? What do we call it?
Elastic.
No, geothermal. And that is, in this case, it's going to be thermal potential because it's going to be, it has the energy to be, when it's in use, it's kinetic, but it's a potential type of energy. All right, so living things, what kind of energy is this? Do we know? This is what we call biomass, okay? And then that would be a type of chemical, right? And then lastly, or almost lastly, we're coming up on this one. Okay, this one is hydrogen fuel cells, and these are when you have hydrogen oxygen reactions. So that's a chemical. Yeah, we do use them. So energy resources can be conserved by reducing the energy needs and by increasing the efficiency of energy use. So what do we call it when we use energy more efficiently or use less energy? Do you know, Darcy?
Energy conservation.
Yes, energy conservation. That's good. All right, so our 3 R's of energy conservation: reduce, you heard this one? Reuse and recycle, right? Okay. This is these are our 3 R's of energy conservation: reduce, reuse, recycle. And power. We're going to look at power real quick. All right, power. Remember these guys? Joules and Watson. Joules, it takes a lot of hard work for Joules to mine the joules. And for Watson, I wonder what Watson had to do to become the most powerful rat in the world. Okay. Power is the rate of doing what? Eunice? Work. Okay. And doing work at a faster rate requires more, Lewis. Or could be, or cause more power, because power is, we're talking about the rate of doing it. So because the word rate is used in that sense, we're looking for power. So to increase power, you can increase the amount of work done in a given time, or you can do a given amount of work in less time. That makes sense, right? So to calculate power, what do we do, Darcy?
Work divided by time.
Work divided by time. Mhm.
Work.
What's it say?
Knowledge equals work
Knowledge.
divided by time.
If you put in a lot of work over a lot of time, do you gain a lot of knowledge?
Yes.
And what does knowledge equal?
Knowledge equals
Equals
power.
Hey, you got it.
Knowledge
So,
is powder.
yep, the SI unit for power is
The what?
the watt. Yep. And 1 watt equals 1 what?
One.
Lewis, do you know? Joule per second. Right. Good job. All right. So, horsepower. This is maybe one of my favorite AI images for the whole year because that is freaking cool. Right. So, 1 horsepower is about how many watts, Eunice?
745.7.
Yeah, about 746. Random. Usually we work in like tens and hundreds, right? Like, what is this? This is a weird number. Okay, it's because in the 1700s, a horse was your most common source of power. So James Watt used that as the basis for comparison to describe power outputs when he built what? What did he build?
Steam engine.
Steam engines, right? Okay. So here is James Watt. Let me look real quick to see. Okay. All right, here's James Watt. I'm going to show you this, and I'm going to actually get something ready for you to see. Come on. I don't know why, but it's been having issues playing stuff this morning. There we go.
Against the backdrop of the Industrial Revolution's dawn,
Of course it's
there
gone.
lived a man whose
Yeah.
inventive genius would spark a profound transformation in human history. James Watt, born in 1736 in Greenock, Scotland, emerged as one of the most influential engineers and inventors of all time. Watt's early years were marked by an insatiable curiosity for all things mechanical. As a young instrument maker, he displayed an innate talent for craftsmanship, which would soon become a hallmark of his engineering prowess. It was this talent that led him to a chance encounter with a malfunctioning steam engine in 1765, a moment that would forever change the course of his life. Upon examining the engine, Watt recognized its inefficiency and pondered the limitations of contemporary steam engines. His keen analytical mind, combined with an unwavering determination to solve this problem, led him to invent the separate condenser in 1769. This brilliant innovation allowed steam engines to operate with unprecedented efficiency by preventing the loss of energy during each cycle. Watt's groundbreaking invention revolutionized industry, transportation, and manufacturing. His steam engine became the backbone of the Industrial Revolution, driving machinery in factories, powering locomotives, and propelling ships. It was a force that not only transformed the economic landscape, but also reshaped society itself. James Watt's contributions extended far beyond the mechanical realm. His tireless work led to the development of standardized measurements for power, with the unit of power, the watt, bearing his name. This symbol of progress became a fundamental concept in science and engineering, ensuring that Watt's legacy would forever be woven into the fabric of human knowledge. Despite facing numerous obstacles, including financial challenges and setbacks, Watt's dedication to engineering excellence remained unyielding. His engines continued to evolve and improve, embodying his relentless pursuit of perfection. James Watt's story is more than a narrative of invention. It is a testament to the power of human innovation and the boundless potential of the human spirit. His enduring legacy serves as a reminder that one individual's determination and ingenuity can catalyze monumental change, shaping the destiny of nations and leaving an indelible mark on the course of human progress. As we reflect upon the vast transformations brought about by the Industrial Revolution, let us remember James Watt as a visionary whose inventions not only powered machines, but also forged the engine of human progress itself. His life story is a timeless inspiration, underscoring the incredible impact of innovation, engineering brilliance, and the unwavering pursuit of excellence. If you found James Watt's video inspirational,
Show y'all.
please consider subscribing because we have a lot more videos like these coming up.
Got my Baylor Bears cup. Now I do have, like I said, I did have some fun videos, but we're not gonna have time for them. I'm gonna put them in your You can find them in your resources. Yeah. All right. Now, this right here, y'all see this?
Yep.
This isn't Watt's engine, but it's got a similar, it works similarly. This is called a Stirling engine. And I just microwave the water in that cup. So the water's really hot. Okay. Now, there's a little diaphragm in here. Do you see that? And as the steam in here heats up, it causes that to expand. And then once I give it a little kick, it's going to keep going because as the steam heats it up, it pushes that arm turns the wheel. It'll get going pretty quickly and it will go as long as it's warm. So this is similar to how some of the steam engines that Watt used functioned. There you go. Look, it's really going now. See?
The heat's pushing up and the force of the movement pushing back down.
Exactly. Smart, right?
Uh-huh.
The cycle. Tick, 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 tick. Very, right? Very cool. All right, gang, you want to come on in? Let's do lab.
Lab 14.
You should put a.
Yeah. Good. We got enough